I sent out a message, not right before class, I sent out a message like a few hours ago about question 8 on exam 3. I guess when I was so I said antiderivatives wouldn't be on the test, and I guess when I was making test 3, my brain just didn't pick up that I was putting an antiderivative problem on there. So question 8 is an antiderivative problem, which I said I wouldn't put on exam 3, so I'm making a question 8 extra credit. The problem was originally with 12 points because I scale the points to make it so it's out of 100. So it won't be 12 extra credit points. It'll probably be like 2 or 3 extra credit points. But just so everybody knows, question 8 on the exam, on exam 3 is extra credit, 2 or 3 points. And I won't make it so that it's mandatory. So if you want to skip that question, it's fine. It might be good practice coming up for the final exam, but you don't have to do it. So thought I'd put that all out there. All right. So also exam 3 is due on what, Wednesday, I think? I'm pretty sure Wednesday was, well, let me go double check because I got the dates all messed up. Yep, Wednesday night, Tuesday night, Tuesday, November 17th at 11:59 p.m. Tuesday at 11:59 p.m. I don't mind extending it to Wednesday. I can do that. Catherine, if you send me a message and remind me, I'll extend it to Wednesday. Early Thanksgiving gift for everybody. Just send me the message. If nobody sends me a message about it, I will forget. My brain is like a goldfish right now. I will forget, but send me the message. You can send it right now if you'd like. And I'll do that. I'll extend it to Wednesday and I'll send everyone a message saying happy early Thanksgiving. Let me pause this for a sec. Back to our regularly scheduled lecture. All right. We're almost at the end here. We have a little bit more to go over. I'm going to kind of skip through some of the stuff that maybe in a regular semester you'd spend more time on, because some of it is just kind of interesting stuff, but not stuff that is vital for your success in future classes. And I want to get to the stuff that is vital for your success in future classes. So some of this I'm going to go kind of fast over, and I'm not going to test you heavily over. But I need to at least show it to you so that I can feel like I did my job as a calculus teacher. So last we'd begun talking about Riemann sums, and we had talked about Riemann sums in the context of, hey, we can make these rectangles to to approximate area under a curve. We can make rectangles to approximate area. And so we did that, and I talked about ways to kind of set up your information and make these rectangles. And now we're going to kind of formalize it. So we started to go into summation notation, and we talked about how summations work, where you have a lower bound and upper bound, and then you're just kind of plugging the numbers in. So you iterate this number down here. You start with 0, which is your lower bound. You plug it in, and then you iterate. So you add 1 to it. So then you're at 1. You plug 1 in. Then you go to 2, and you plug 2 in, and you go all the way up till you have your upper bound. So we talked about doing that, and then I said, okay, well then get a little more complicated. There's these formulas that are involved where, like, if you want, you can just use these formulas and then plug in your upper bound at the end. So we did a few problems like that. I'm going to get into some interesting notation here. So once again, on an interval, these are always on intervals a to b. And when we talk about the number of rectangles we're making, when we're making those rectangles to approximate area, we say that the number of rectangles is n. And then we talked about the width of each of those rectangles. We called it delta x, and we did b minus a over n. So it's like the start of your interval, the end of your interval minus the start of your interval divided by the number of rectangles you have. That'll tell you how wide each of your rectangles needs to be. I'm going to go back to this example real quick. Maybe this example real quick. Take a screenshot of it, and I'm going to do some fancy work here. Maybe I should have cropped that thing first. Oh well. Oh well. So I want us to think about what these sums would look like if we wrote them in this summation notation. Because what we ended up doing was adding up a bunch of areas, right? We added up a bunch of areas, and that gave us this approximate area in here. We added up the area of each of these rectangles. It gave us an approximate area. So there must be a way, if we're doing a sum and we have a sum notation, there has to be a way to combine the two ideas, and there is. There's a way to combine this idea of summation notation with the idea that approximating area is adding up a bunch of rectangles. We're only going to talk about the right-hand Riemann sums, so we're going to ignore this stuff down here. We're just going to talk about the right-hand Riemann sums. So I want us to think about what each of these rectangles really are. What each of these rectangles really are. Clearly we have an x value that we're plugging in. And maybe what I'll do, maybe I'll take this other example is a little less messy. Maybe I'll take this one. All right, let's try this. All right, so we know we're working with a sum here. We know we want to make this into a sum. The right-hand Riemann sums, we say the notation is R sub n. So this is R for right-hand Riemann sum, and n is the number of rectangles. And all of the Riemann sums, when you're in your n notation, so they go to n, that's the number of rectangles. And we start with 1. Typically we use k or I. I'm going to use k. So we're going to sum up a bunch of rectangles. We're going to start with 1 rectangle. We're going to go all the way up to n rectangles. And now I'm looking over here at what we did before and trying to figure out how I can use this idea of a sum over here. Now clearly with each of these, we had a height and a width, and we multiplied these two values together to get the area, right? We took the height and the width, and we got an area. So we just need to figure out how to express the height and the width in a notation that we could use for this formula. Now the width of each rectangle, that was already given to us, right? Delta x was the width of each rectangle. It's really the height that we have to worry about. The height we got by plugging the x value into this equation up here, right? Into this equation. Now, for our first rectangle, and this interval that we looked at here, this interval was from -2 to 7. But our first x value was -0.5 because we were doing right-hand rectangles. The rectangles started on the right-hand side. So in the case where k equals 1, in our first rectangle, we don't want the height to be exactly the start of our interval, right? We don't want to start at -2. We want to plug in -0.5. And the height, one more time, this comes from plugging in your x value to the original function. It's like f of the x value. So for our first rectangle, we're starting at the right end of our interval, right? Just pointing our right end of our interval. But we don't want to actually go and just plug in a. We don't want to just plug in a because a would give us -2 in this case, but we want to get to -0.5. We want to go to -2 and then jump delta x away first before plugging it in. We want to jump delta x away before plugging it in. Now, if we just made our formula this, that would work for the first rectangle. So like if we look over here, this would work. F of a plus delta x times delta x would work for our first rectangle. Here, a was -2. So in this case, f of x is 2x squared plus 3. F of a plus delta x, a was -2, delta x was 1.5 in this example. So this would be f of -2 plus 1.5, which would be f of -0.5, which is exactly what we had here. That would have worked. But when you go and you make k equal to 2, it's not going to work because you're not going to get 1. You're not going to get 1, and we want 1 to be the x value. Right? If you're not following along, just try to follow along as best as possible with this. It's not the end of the world if you don't 100% understand what's happening, but I want to give some justification to what's happening. The idea is you multiply this delta x by how many rectangles you're on. So if you're on your third rectangle, you want to add delta x 3 times. So third rectangle, that would mean k is equal to 3. So f of a plus delta x times 3. That's what our k is. This should give us, if I'm looking at my third rectangle here, it should give me 2.5 on the inside. So our a was -2, our delta x is 1.5 times 3. What this is really doing is it's getting us to this point right here. It's jumping 1.5 each time to get us to this third rectangle. So this would be -2 plus, that would be 4.5, which is f of 2.5, which is the x value we were going for. I know this is confusing, but this is all to say that for the right-hand Riemann sums, the formula is f of a plus delta x times k times delta x. Now, sometimes this gets rewritten a little bit differently. All right, so this is the formal definition of a Riemann sum, of a right-hand Riemann sum. This is the formal way we define it. Sometimes it looks different. If you look this up online, there's a chance that you'll see some different notation here. I wouldn't look it up online. There's a lot of very confusing notation. But sometimes, move this up a little. One of the other ways that I would write this, because delta x doesn't change ever, it's basically a constant, right? The delta x can come out front. And then really you're just adding up the sum of all the function values and multiplying by delta x at the end. This is the formal definition of a right-hand Riemann sum. It is summing up the areas of the rectangles. This is height times width added up for n rectangles. It doesn't look that way, but that's what it is. It's really fancy notation, and it's used in defining what we will eventually talk about as a definite integral. So I know this is very complicated notation. Like I said, I need to explain it to feel like I've done my job as a calculus teacher. Try to just vaguely understand that this notation is adding up areas of rectangles. And I kind of went over what this formula means. So I'm going to go ahead and use this notation to show you what this looks like. So if I'm using this fun notation, we're going to use right-hand Riemann sums with 6 subdivisions to approximate the area under the curve x squared plus 1 from x equals -2 to 2. Your first step here is finding delta x. Right, we're using the we could use a table here, but I want you to get used to the notation, and that's why we're using notation instead of the table, just to kind of so you can understand the connection between the notation and the table. Or maybe a better way of doing this, I could actually use this exact problem here. You know what? That's what I'm going to do. I'm going to use this exact same problem to show you how to do it with summation notation. Right, the same exact problem we did before, but this time, I'm just going on a whim here, guys, but this time with summation notation. This is the exact problem we did on Monday of last week. So your first step, find delta x, just like you did before. Right? You have your A and your B. We're looking at 2x squared plus 3. We want 6 rectangles and right-hand endpoints. So your delta x is b minus a over n. So 7 minus -2 over n is the number of rectangles, so 6. Nine over 6 is 1.5. Step 2 is plugging everything in to the R sub n formula. What we have here, we know A is -2, we know B is 7, N is 6, and our delta X is 1.5. Okay. The formula I gave you for R sub N was this. So our delta X is 1.5. So I'm going to put 1.5 out here. Our N is 6. So I'm going to put 6 up here. A is -2, so we have f of -2. Oops. Right, so I'm just kind of trying to color code for you so you can see where this is all coming from. Our delta X is 1.5. And then K is just going to be K. I guess I don't need to color code K. I can just leave K as black. All right. I'm going to iterate this. So I'm going to plug in k, starting at 1, going all the way to 6. So I have, when k is 1, this is 1.5 times 1. I'm going to do this 6 times. I'm going to plug in, and it's going to stay the same. I have plugged in a, I plugged in delta x. I'm going to change k each time I do this. And I'm going to have a string of stuff here. So f of -2 plus 1.5 times 2 plus, same thing, but now k is equal to 3 plus. And you can kind of see what's happening here. I'll just write this, -2 plus 1.5 times, now k is 5. Now, looking at these, just do the insides. You're just going to leave the f's in there, but you're going to do the insides. -2 plus 1.5. That's -0.5. Plus -2 plus, this will be 3. That would be 1. -2 plus 4.5 would be 2.5. -2 plus 6 is 4. -2 plus, what was that, 7.5 would be 5.5. -2 plus 7, or plus 9 would be 7. And I want you to notice something. Even though it was complicated, these x values that you plug into the function, these x values are the same. -0.5, 1, 2.5, 4, 5.5, 7. Those x values all come out to be the same. And when we plug in these x values to the function, just so we all have it here, is 2x squared plus 3. When you plug those numbers in, you're going to get the same heights. So plugging in -0.5, so you have 2 times -0.5 squared plus 3. Plus, now we're plugging in 1 to the function. 2 times 1 squared plus 3. Plugging in 2.5. 2 times 2.5 squared plus 3. right? And then I'm going to plug in each of these guys individually. And I know I've already done it on the other side, but I'm going to do it again on my calculator, just pretending I'm doing it from scratch. So I have 3.5 plus, now if I do it with 1, let's see, I get 5. $15.5, 35, 63.5, 101. And oh, look, those are the same as the heights of the rectangles. And then, I mean, I'm not going to distribute this, but if you could imagine, if I distributed the 1.5 to each of these, that would just be multiplying each of these heights by the delta x and giving me an area of the rectangle. If I add up all these heights ahead of time and then multiply by delta x at the very end, so if I take and add up the heights and then multiply by 1.5, you'll still get 335.25. Like if I do 3.5 plus 5 plus 15.5 plus 35 plus 63.5 plus 101, I get what did I do wrong in here? 3.55, 15. Oh no, that came out right. Okay. I get 223.5. Multiply that by 1.5 and you get, so if you add up all the heights and then multiply by 1.5, you get 335.25. So down here, when I do this, you still come out to the same area. Right. So somebody in the chat said, that's crazy to me how that works out perfectly. It is crazy. It works out perfectly. And it's about making it precise. It's about taking this table idea and making it into one formula. That's what mathematicians are all about. We're all about, hey, yeah, you could organize your material like this. Oops, pointer. Like this. Or we can make it into one fun looking formula and then go from there and make it so that we could write all of that in one sentence. So literally, this entire sentence right here represents this entire table, which is pretty nuts. I forgot to push record again. That's okay, I didn't go very far. So here's the big idea, I guess. This is if you have n rectangles. And this gives us an approximation. I already said this wasn't going to give us an exact area, but this gives us an approximation. I can get more precise by finding more rectangles. The more rectangles I do, the more precise my area is going to get. Right? The more rectangles I do, the more precise my area gets. If I have infinitely many rectangles, I end up with a precise area, an exact area, if you will. Right? If I take the limit as n goes to infinity, that area becomes exact. So this process gets kind of complicated. Debating, like I said, I'm trying to debate like how far into this I want you to see how this works. I want you to see how this looks. At the same time, I don't want to give so much information that it becomes overwhelming. how much to give before it gets overwhelming. It gets overwhelming kind of quickly here. So I think where I will stop with this is like, this is what the process looks like. And then if you took a limit as n goes to infinity, that this would get more and more exact. And we already talked about how we could make these formulas that had n's in them, right? So we don't necessarily need to even have an n value. We can have this come out to just have n's in it. If I look at what was going on over here, let's pretend I didn't have a 6 here. Let's pretend I didn't have a 6. Let's, because really, this was r sub 6. This was r sub 6 here. But if it were just r sub n, and I didn't know how many rectangles there were, right? If it were still on the interval -2 to, what was it? -2 to 7, but we didn't know how many rectangles there were. We didn't have an exact number we were going for. We could still find our delta x, to be b minus a over n, but we don't have an n this time. So 7 minus -2 over just n, 9 over n. This is a, this is b. You could plug this in. If your delta x is 9 over n, 9 over n, k equals 1 to n, you could leave your formula, if a was -2, 9 over n times k, you could do this whole formula. You could plug this in, where is it, to your function, and eventually get this all down using those rules from before to a formula that just has n's. Your formula would end up looking something like this down here, where you just have n's, and then you could plug in any n you wanted. I'm not going to do the process. It's pretty algebraically intense. That's the problem here. It's not even mathematically intense. It's just algebraically intense, and that's why I'm hesitant to go through an entire example with one. But you could get it down so that it just had n's in it. And then you can plug in whatever n you want and get an answer for what the approximate area would be. And I'm going to leave it there. It gets a little too complicated for me to want to spend time talking about it. But the big takeaway is that you could take the limit as n goes to infinity. All right, this is the next section. You could take the limit as n goes to infinity of a Riemann sum and make infinitely many rectangles. And if you have infinitely many rectangles, you have an exact area. And we call that exact area a definite integral. A definite integral. So the exact area under a curve, if you took a limit and you let n go to infinity, that exact area comes out to be the idea of an integral. And it's interesting because limits were also used for us in derivatives, right? So derivatives were giving us the slope of the tangent line. And remember, so we said that f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Right? This is the idea of a derivative. Antiderivatives relate to the idea of integrals, and we're taking the pieces together to make the connection between the two. But an integral also uses limits, and it takes an idea of rectangles And it says if you let there be infinitely many rectangles, and we take the limit, then we can find an exact area. So limits have this connection to both the idea of antiderivatives, which will relate to this idea of integrals we're talking about, and they also relate to derivatives, which we spent the first half of the course talking about. So the definite integral of f on an interval a to b is going to be that area under the curve. And that exact area is just the limit as we let there be infinitely many rectangles. We just take infinitely many rectangles, and that's going to give us the actual area under a curve. And just like it was with derivatives, where it's like, yeah, you have this formula, but like we only used that for a little while, right? We only used this part right here just a few times just to see how it worked, and then we got rules. The same thing is going to happen here, and that's why I'm hesitant to go too far into this, because yes, we could technically go through this really lengthy process. Let me just, I'll show you actually. I'll turn on my back camera. I guess people in the future watching this won't be able to see this because I'm going to use my camera, but I'll be right back. So let's talk about where all what this all means. What all this notation here means, because this is what you're going to get used to. All right. So this A and B, these are the start and end of your interval, just like it was when we were talking about it before. A and B are the start and end of your area. This is where you start, this is where you end. So we call this guy right here the upper bound. A is your lower bound. This guy right here, this little looks like an S. We call this an integral symbol. Right? It's kind of like it's like a stretched out S. Which is interesting, right? Because I had said that the sigma was like, it stood for sum, like it's like Greek letter S essentially. And then we take a limit and then it turns into like an English S for sum. Let's use pink here. This guy right here, we call the integrand. That's the function we're integrating. It's the function we're looking at and taking the area below the curve. Function call it the integrand. And this dx at the end tells us which variable we are integrating with respect to. It also is like the period at the end of a sentence. It tells us where the integral ends. So like if you have a dx, that means the variable is x. If you have a dy, the variable is y. If you have a dA, that would mean the variable is a. So the dx at the end just tells you what variable you are integrating with respect to. It also tells you where the integral ends. The way you would say this out loud is the integral of a to b of f of x dx. So if you're saying this out loud, that's how you'd say it. The integral of a to b, sorry, not of a to b, from a to b, from the integral from a to b of f of x dx. And it's just the limit, it's the limit of the Riemann sums once you've plugged in all the ends and everything. Once again, I don't think I'm going to go into that detail because it's very complicated and it takes up a lot of time. So let me really emphasize here what I'd like you to know. I'd like you to know that this integral is the sum of infinitely many rectangles. That this right here represents a sum of infinitely many rectangles. I'd like you to know that you could always, that the way that we start talking about area is by making these tables and finding a few rectangles. And that the idea behind an integral is that you find infinitely many rectangles and you use a formula for it. I'm not going to actually go through the process of actually doing these because I think it's going to be more confusing and I think it's going to be less of a good use of time than us actually just skipping the part where we talk about the build up and we go straight to the integrals. So I am going to skip some of that discussion there. So when we talk about integrals, all the things that when we've talked about area, all the things we've talked about have been above the x-axis. But when we talk about integrals, if something ends up below the x-axis, we say that it has negative area. So anything below the x-axis counts as negative area. Anything above the x-axis counts as positive area. So, if you're really trying to find area, I'll draw a small picture here. This is the line negative x. Let's say you're going to 5. Let's say you're trying to find the area under the curve and you have this line negative x. If you take the integral from 0 to 5, so starting here at 0, going to 5 of this function negative x dx, it would come out to be negative 25 over 2. Right? And this makes sense too, right? You can find your delta x's and everything, but what's going to happen is that your function values are going to be negative. So when you go to put the height of your rectangle in, just imagine the height of your rectangle, right, is going to be negative. You're going to get a negative value here. So when you add up a bunch of negative values, you're going to get a negative area. So if we really wanted to talk about the area of this triangle, we wouldn't just be able to say, oh, take the integral from 0 to 5 of negative x dx. You can't just do that because it'll give you a negative value, and the area shouldn't ever really be negative, right? The area of this triangle would actually be the negative of this, or the absolute value of it. So the actual area of this triangle would be the negative of this. So anything below, if you're trying to just look at area, if something turns out to be below the x-axis, then you're going to need to put a negative in front of it to make the area positive. If you're asked about area. Integrals in general, the way that they're determined, because they are determined on these rectangles, and the rectangles are based on the function value, if it comes out below the x-axis, that area will look negative. In this example, we want to use definite integrals to represent the area of the shaded region. So this area right here, this is the function e to the x from 1 to 2. It's all above the x-axis. This is all positive. So the area here would just flat out be the integral from 1 to 2 of e to the x dx. On the other hand, if we look at this example, and we're trying to find this area from 0 to 4, this shaded area here, all of this is below the x-axis. So all of this, if I took the integral, would come out to be negative, right? If I went from 0 to 4, square root x minus 2 dx, this would come out to be a negative value because it's below the x-axis. So the area itself, I would want to put a negative in front of it to make it so that area comes out positive. If I have something where I have positive and negative area, these are actually equal amounts of positive and negative here. So if I just flat out took an integral and I went from 0 to 2 pi of sine x dx, this would come out to be 0. I'm just going to tell you, it would come out to be 0. Because this positive area and this negative area, all those little baby rectangles would cancel each other out, and the positives and the negatives would cancel, and it would come out to 0. So if you wanted to actually know the area here, this area would be positive. So from 0 to, this is pi right here. Pi is where, this is 2 pi. So from 0 to pi, the area is already positive. To make this second bit of area positive, you'd be subtracting it. So when you go from pi to 2 pi, you subtract it to make the area positive. Right, so There's nothing wrong with integrals giving us, doing this signed thing here. There's nothing wrong with the fact that this integral equals 0. And sometimes this is what we care about. Sometimes we don't care about area. Sometimes we're going to care about what the actual value comes out to be. But it's important to understand what integrals interpret area as. That if you take an integral from 0 to 2 pi, it's not just everything trapped in here. It doesn't just add up everything in here. What an integral will do is it'll take area that is positive and area that is negative, and it adds it all together. So it's not going to tell you actual area. It's going to kind of tell you like net area. You can kind of think of an integral as giving you net area. And then if you wanted to actually know just the area, that you will have to negate negative area to get to the real answer of how much area is there. This is something that takes practice. This is something that takes practice. So if I look at this picture here, I have a function, negative x squared plus 4, from negative 3 to 3. And I want to find the area. I want to use definite integrals to represent the area of these regions. So this is negative 3. Here is negative 2. Here's 2. Here's 3. Both of these areas right here are negative. What that means, once again, is if I take the integral from negative 3 to negative 2 of this function, it'll give me a negative number. If I want to find actual area here, I would have to negate this negative. So I'll have to make it negative ahead of time from negative 3 to negative 2 of my function, which is x squared plus 4. So I could type that in there. Right? That will be this area here. Because this area is above the x-axis, this is positive. It already comes out positive when you go to do your integral. So when you go from negative 2 to positive 2, that's positive area. Over here again, this chunk here would come out to be negative area, so we would put a negative in front of it to negate the negative when we go from 2 to 3. So if we're trying to represent area, and this is all about representing area with integrals, once again, the important thing when representing area with integrals is understanding that those areas could come out to be negative, so you would have to make them unnegative. It takes time. So let's go back to this notation and what this means. And let's use geometry to evaluate some integrals. Here we have a function. So let's just say the function is y equals the square root of 4 minus x squared. This might look familiar to you. Maybe it doesn't look familiar to you. But if you square both sides of this, y squared equals 4 minus x squared, and you add the x squared to the other side, this might look more familiar. This right here is secretly the formula of a circle. This is the equation of a circle centered at the origin with radius 2. X squared plus y squared equals r squared, if that sounds familiar. So very secretly, if you look at this, this is actually the equation of a circle. Now it's the upper half of the circle because it only has the positive here. So if I draw a picture, this is really what the picture would look like. It's the upper half of a circle. This is y equals 4 minus x squared. Negative 2, positive 2. It's a positive square root, so it's only the upper half of the circle. So if my integral is going from 0 to 2, that means I'm looking at this portion of the circle. I want to find the area of this portion of that circle. Well, that's just a quarter of a circle, right? We're using geometry here. This is just a quarter of a circle. That's something we can do. A quarter of a circle. Well, the area of a circle of a whole circle is pi r squared. So if it's a quarter of a circle, then it's just 1/4 pi r squared, and r is 2 here. And this just comes out to be pi. If we use geometry again on a different example, 1 minus the absolute value of x is a graph that looks like this. Right? This is the graph of 1 minus the absolute value of x. The x-intercepts, this is -1 and 1 here. So if I'm looking at the area between -1 and 1 under the curve, I can use some geometry here. This is simply a triangle. The y-intercept here would be 1. This is the graph of 1 minus the absolute value of x. If reviewing graphing is something you might want to do, that's something you could do. But I'm going to tell you that this is the graph of 1 minus the absolute value of x, and that the y-intercept here would be 1. So you're looking at a triangle whose height is 1. And then the base, this is 1, this is 1. So the base of this triangle is actually 2. So this is really just the area of a triangle, 1/2 base times height. So that's 1/2 base times height. So with some of these integrals, we can do these geometrically if they're the right type. If they're the right type of integral, we can do them geometrically and find the area under the curve. Something I want to point out here, if I said instead the area from 0 to 2, or not the area, if I said the integral, what if we did this instead? If we said from 0 to 2 and we wanted the integral, and I have a picture drawn for you. Let's say I draw you a picture and I show you that the picture looks like this. Hell, I could even make this a little easier. Let me make it even nicer. If I go from 0 to 2 and I just have 1 minus x, not even absolute value, just 1 minus x dx. This is just a line, right? Just a line. This is y equals 1 minus x. Y-intercept is 1. It goes beneath the, it has an x-intercept of -1. Not -1. +1. +1 and 2. And I wanted this integral. And I'm doing it geometrically, right? I have 2 different areas here. Now, the integral itself, if I'm doing this geometrically, I have to remember that this should be positive and this should be negative. I'm going from 0 to 2. 0 to 2. This portion is positive. This portion is negative. The area of this triangle, base of 1, height of 1, 1/2 base times height. The area of that triangle is 1/2. This triangle down here is a similar thing, right? This is 1. This is 1. The area of this triangle is 1/2 base times height, which would come out to be 1/2. However, in the terms of an integral, right, the area here is 1/2 plus 1/2. That would be the area, but the integral would interpret this as negative. So if I'm writing this in terms of an integral, it would see this guy as positive, but it's going to see this guy as negative. So the integral would say that the area here is 0. The value of it is 0, because it views that any area under the x-axis is negative. So let's get into a few rules here. And these rules relate to definite integrals. And sometimes it makes sense to think of them in terms of area, and sometimes it does not. But here are some rules. If you start at the same point that you end, if your starting point and your end point are the same, this is A, there's no area. It's 0. It doesn't matter what your function is. If you start and end in the same place, if your lower bound and upper bound are the same, you don't have any area. It is 0. Here's another rule. If you want to flip your bounds, so notice that you have from A to B. If you want to go from B to A instead, you can do that if you make the integral negative. You can make the integral negative and flip the bounds. If you have a constant, you can take a constant out front of an integral. If you're adding or subtracting two functions within an integral, you can split this up. So you could make it a to b of f of x dx plus or minus the integral of a to b of g of x dx. So you can split these up. This next one, I kind of want to show a tiny bit of a picture here. So imagine I have some graph and it really doesn't matter what my graph is. If I'm going to A to B and I'm looking at this area from A to B, I can always split it up at some part C and take this piece and add them together. Right? If I go from A to C and take this piece plus the area from C to B, this piece, and add them together, that's just the area from A to B of f of x dx. I can take those two areas and add them together. So I can split it up. And here's the interesting thing. This actually doesn't matter what C is. C could actually be out here outside of the interval and it would all work out, crazy enough. But it's just a fun fact. If your function is greater than 0, that's saying that your function is positive. So here's a function that's positive because it's above the x-axis. Then your area is going to be positive. This is something we already talked about. So the integral's value will be greater than or equal to 0. If your function is positive on an entire interval, then the integral will be positive. If your function is negative, so here is a negative function, below the x-axis. If your function is below the x-axis on an entire interval, then you're going to have a negative value for your integral. This last one is just kind of more confusing than it's worth, and I'm just going to ignore it. So I want to show how some of these rules work. Right. Show how some of these rules work. We're given some values here. We have two functions, f of x and g of x. And we know from 0 to 5, the value is 10. From 5 to 7, the value is 3. And then we know something about g of x. But if I look at this first one, I'm asked about from 0 to 7. What is the value of this integral from 0 to 7? So let's do a little bit of thinking here. Well, if I draw a picture, right? I don't know, just draw some picture f of x. Here's 5, here's 7. This right here, from 0 to 5, this area was 10. From 5 to 7, this area was 3. So from 0 to 7, well, I could just add those up, right? That actually follows our rule. That follows this rule. Where is it? Where are you? Right in here, where it says if you go from A to C and then C to B, then you get that entire area. So if I take the integral from 0 to 5 plus the integral from 5 to 7, that's the same thing as going from 0 to 7, because they stop at 5, begin at 5. So we have 10 plus 3 gives us 13. For this next one, we have to think about the rules that we have. I have an integral that goes from 0 to 5. This one wants from 5 to 0. But remember, there's that rule that says if you make it negative, you can flip the bounds. By making it negative, I can flip the bounds. And I know what the integral from 0 to 5 is. It's 10. So this would be negative 10. Because the value of this part was 10. What if we wanted to go from 5 to 7 of 2 f of x dx? Well, we could take this 2 out front. Then the 5 to 7 part, that's just right here, right? If we took that out front, if we took the 2 out front, the integral from 5 to 7 of f of x dx was 3. So this would be 2 times 3, which is 6. With this last one, we can split it apart. So we go from 0 to 5 of f of x dx minus, and then we'll go from 0 to 5 of 4 g of x dx. And let's look at what we're given here. We do have 0 to 5 f of x dx. We know that one is 10. For this last one, we don't know what 4g of x would be, but we can move the 4 out front. So we have 4 integral from 0 to 5 of g of x dx. And we were told up here that that value was 2. So that's 10 minus 8. The value is 2. These types of problems right here that I'm doing are to kind of get you familiar with the rules and how flipping things around works, right? How manipulating these rules works. So let's make it a little more challenging. Make it a tiny bit more challenging. So, make sure that's plugged in. We're given some information about a function h, just h this time. And we want to find this integral from -3 to 0. So if we look at what we're given, we have to think about what we can do here to figure out this integral. Now, one of the tactics we had used in the previous problem was we had this one where it was like if you have from a to c of f of x dx plus c to b of f of x dx, that this was the integral from a to b of f of x dx. But that requires that you have some value c that's at the end point and the starting point of the next integral. If we wanted to use this here to evaluate this integral, well, we'd have to be kind of tricky. We'd want our a to be -3. We'd want our b to be 0. Now, this looks like a promising starting point here. We have from -3 to 4. That looks promising because it starts with -3. But the problem is it doesn't end with 0, right? And I can't use these two together because look at how the c's have to line up. It has to be the end point and the starting point. But we did say that if we make an integral negative, that we could flip those bounds. So if we make that integral negative, we're really making, I guess the better way of writing this would be, this would be -2. So you're making the value negative and flipping the bounds. Making the value negative and flipping the bounds. is one way you could look at this, because then you can add these guys together. But let's say you don't like that. Let's say we don't want to think that tricky. Let's not think tricky if we don't want to think tricky. Here's my function, h of t. From -3 to 4, is this amount. What we're looking for is from 0 to -3. So that's this amount. This guy over here is from 0 to 4. If we know what the purple amount is, and we know what the green amount is, we can find the blue amount, right? We could find that blue amount, because it would look to be that integral from -3 to 0 of h of t dt plus integral from 0 to 4 of h of t dt equals the integral from -3 to 4 of h of t dt. If these two things added together give us purple, well, then to find blue, you could just subtract. You could take the purple area, subtract the green area, and that would leave you with the blue area. Right? The purple area minus the green area leaves you with this blue area here. So this is the same thing as taking the integral from -3 to 4 of h of t dt and subtracting out the 0 to 4 part, which we don't need. Right? For this next part down here, you actually already have all the information. So from 0 to 4, that was already given in the problem. That was 2. 0 to -3, you just did in the previous part. Sorry, -3 to 0, you just did in the previous part. We found that one to be 3. So this is just 2 minus 3, which is -1. Part C is very similar to part A. And kind of what I want you to think about. So you have this one way of looking at it where you can look at it as these areas and stuff, but you can also look at it. Let me just write this down. I'm writing everything we were given. So we have that this one was 5. This is just what was given in the problem. H of t dt is 2. 0 to 6. With each of these, I can flip the bounds and make the number negative, or opposite rather. So if I go from 4 to negative 3, that would be negative 5. With this one, I could go from 4 to 0, and it would be negative 2. For this one, I could go from 6 to 0, and it was negative 3, so this would become positive 3. I could take any of those and flip them around and make the value at the opposite sign. I could flip the bounds and make the value the opposite sign. Using either this idea, because right now we have 6 different integrals we can work with. You can use either this idea or this idea here of drawing a picture. Figure out this value right here. And then try doing the same thing with part D. Try doing C and D here. Using the values you're given, maybe this idea here, or maybe the idea I used up here to find part A, figure out parts C and D. I'm going to give you a few minutes for that. Are we getting any answers on part C or D? I got, so negative 5 for C. Yep, 5. C is negative 5. C is negative 5. Here's one way of doing it. So if we want to go from 4 to 6, we could take this guy who goes from 4 to 0, and this one goes from 0 to 6. So we could say that this is the same thing as going from 4 to 0 plus the integral from 0 to 6, even though it doesn't look right. All right, I know it doesn't look right because 0 is not between 4 and 6. It still fits within those rules. So 4 to 0 was negative 2. And then 0 to 6 was negative 3. So negative 5. And what about for D? Someone got 0? Yeah. So I agree with 0. So with negative 3 to 6, right? There's a few things here. We could go from this guy here. We could go negative 3 to 4 was 5, and we have 4 to 6. So you could go this guy plus this guy. You could do, you have negative 3 to 0 here, and then you could go 0 to 6, 3 plus negative 3. It doesn't really matter how you break this up. But if you go negative 3 to 4 plus 4 to 6, negative 3 to 4 was 5. 4 to 6 was negative 5. And it doesn't matter because you could do this. You could also have done it with other breakdowns. Either way, it's going to come out to be the same thing. It's going to come out to be 0. So if you did the breakdown from negative 3 to 0 and then 0 to 6, you're going to get 0 because you'd get 3 plus negative 3. If you did it this way, 5 plus negative 5. Either way, it's all going to come out to 0. Excellent. And while I was having you guys do that, I just checked my email real quick, and I got an email from a student that said it's not question 8 that's the antiderivative question, it's question 7, which is right. So I don't know how to make an email. I'll email about that. I previously had an exam. The exam I was going to give you guys had 8 questions on it. And then at the last minute, I decided one of the questions was too hard and I took it out. So the exam I was looking at had that question on it still. So it's actually question 7 that has the antiderivatives. I will send out an email about that one. My bad for keeping an old version, because when I give out an exam, I go through all the problems, make sure they all work out. So that was what I was looking at when I looked at it this morning, and it still had the old question on there. Okay. All right. So for example 4.2.8, you have a graph and you're asked to find values of integrals, which requires really just doing a lot of geometry type stuff. So let's look at this first one. Going from -7 to -3. So -7's out here, -3 is here. This is a half circle. So it's above the x-axis. It should come out to be positive, and it's a half circle with what radius? What radius does this half circle have? Two. Yep. So if we're finding the value of this, because that would be this area here, it's 1/2 pi, and then r is 2 squared. So the value of that integral, the value from -7 to -3 of f of x dx is 2 pi. If you go from -3 to 2, we're looking at this area here. Now, we're looking at that area there, and I want you to think about the signs involved, like if it's above or below the x-axis. Try to find the value of this integral. This integral, remember, if something's below the x-axis, that the value would be negative. And if it's above the x-axis, the value is positive. So try to figure this one out. What should the value of this integral, which is from, again, -3 to 2 of f of x dx, what should that be? I'm here in a -5. Let's see here. So this y value down here would be -3. So it has to be negative because it's below the x-axis. So I know it's going to be negative. And then the base of this guy, from here to here, that's 3 units. And then from here to here is 2 units. So we know this distance here is 5 units. And then below the x-axis, for the height of it, so we already have the negative taken care of. But it's the height of the triangle would be 3 units tall. So this area, -1/2 base times height, This would be negative 15 over 2 because it's a triangle. Oh, okay, yeah. So if you put 2 instead of, yeah. So if you have the 3 there, then it'll give you the negative 15 over 2. From 2 to 7. From 2 to 7. Let's see. Now, this guy has a 2 in front. We can take that 2 out front, right? We can make this 2, and then the integral from 2 to 7 of f of x dx. We can really think of this as 2 different shapes, right? There's this guy right here from 2 to 4. And then there's also the integral that goes from 4 to 7. The one from 2 to 4, it's a right triangle, right? Base is 2, height is 2. The 1/2 base times height. For the 4 to 7 part, this is a rectangle. Its length from 4 to 7, that's 3. And then its height is 2. So here we have 2 plus 6. Right? This guy is 2. This guy is 6. So the integral from 2 to 7 of f of x dx is 8. So if we have this integral from 2 to 7 of 2 f of x, and we take the 2 out in front, we know this part right here is 8. This is just 2 times 8, which is 16. For this next one, notice that the bounds don't make sense graphically. The bounds don't make sense graphically. So if the bounds don't make sense graphically, I can make those bounds make sense by making the integral negative. So I can go from 5 to 7, make that integral negative. From 5 to 7, 5 is right here. That's just a box, right? That's just this distance here from 5 to 7 is a 2. This is a 2. So you have negative and then the area of that rectangle for negative 4. The last one's just a trick one. If your bounds are the same, it's 0. The area is 0. It doesn't matter where your bounds are. The area is 0. Yep, 0. So I know that the information seems a bit scattered right now. All right, the information seems a bit scattered, and I promise it all comes together. There's just a few pieces we have to get out there before we can put all this information together into one nice, neat package. But the thing I want you to remember from this idea is that the integrals are simply taking a bunch of those rectangles and adding them up infinitely many of those rectangles instead, though. So That's why these areas turn out negative when we talk about the integral, because these areas would be negative. If you tried plugging the function value in, you'd get a negative value, which makes that area of that rectangle appear negative. So I just want you to keep that in mind, that these integrals interpret things below the curve as being negative, above the curve as being positive. And that geometrically is one way we can talk about this, but there's going to be functions that we can't geometrically talk about. Like, for instance, like if I'm looking at like the function x squared and I want to find like this area in here, I don't really have a geometric way of interpreting this, right? This isn't a triangle. This is not a circle. This isn't really anything that I can interpret geometrically. So we need to have better methods than just trying to mishmash together a bunch of ideas and geometry in order to get these areas. Sometimes it works with the right graphs, right? But this method here that we're using isn't going to be applicable in every situation. So we need to build up the tools so that we can use it in any situation, that we can figure out these areas in any situation. And that's what we're going to get into going into these next sections. All right. So I'm going to send out an email right now about the fact that I messed up the numbers. Your exam, I will extend the due date to Wednesday. I think Catherine sent me an email, so we're good. Yes. So I will extend that due date till Wednesday, and I will see you guys again on Wednesday. Hopefully you have a fantastic week. Happy almost Thanksgiving. We're almost there. A little bit longer than Thanksgiving. All right. Bye, everyone. See you Wednesday.